first, anybody have any homework questions or questions about the exam or anything? Well, let me get this up here. So exam 1 is on Friday. And the topics are everything up through rigid body statics. So no centroids. All right, any homework questions or exam questions? All right, so last time, back to centroids. So last time, I gave the integral definitions of the centroids. But you won't ever have to use those in this class. And there are 3 reasons for that. Or let's say 3 facts combine to make the integral definition unnecessary for us, you know. The first one is what I said last time. Once you do that integral derivation one time, you can just use the algebraic formula you come up with. So if you do the integral once, you can come up with an algebraic formula for that shape. So for example, we did a right triangle and we figured out that the distance from, you know, the perpendicular side to the centroid is L over 3, I guess base over 3. And the distance this way from the perpendicular side to the centroid is H over 3. And now that we have that, you know, there's no reason for the integral anymore for a right triangle. Second, centroids always lie on any line, that's if we're talking about 2D, or plane in 3D of symmetry. Okay, so if you can find in 2D a line of symmetry or in 3D a plane of symmetry, then you don't have to worry about the centroid in that plane. So I guess along that axis, not in that plane. But let me show you what I mean. So for example, if you're shape is this rectangle. Can you find any lines of symmetry? There's one here. There's one here. Since the centroid has to lie on both of those lines of symmetry, this centroid is fully defined, and we don't have to do any more calculations. Okay? There's only one place where those two lines of symmetry, where you're on both of those two lines of symmetry, it's at the intersection. The same thing with a circular shape. So there's a line of symmetry there, a line of symmetry there, there's infinitely many of these, but they all intersect at the same spot, and so that's the centroid of this 2D shape. Okay. What about 3D? So let's think about like a rectangular solid. There's one plane of symmetry here. There's one plane of symmetry here. There's one plane of symmetry here. I'm not going to fill this in because it would be make a big mess, but and these three planes only intersect at a single point, and that's the centroid. Okay, so in 2D, if you know any two lines of symmetry, that fully specifies the centroid. In 3D, so in 2D, you need two lines of symmetry to fully determine the centroid location. In 3D, you need three planes of symmetry. And the third thing that's going to help us is we're going to have some formulas that are going to allow us to calculate the centroids of complicated shapes that are built up from simple shapes. Okay. So the sum formulas will let us calculate the centroids of compound, let's say, shapes made up of simple shapes. Okay, so the first thing I'm going to do is just give you formulas for some of these common shapes. So centroid formulas for common shapes. Well, we did the calculation for a right triangle. I'll put that one first. So if this whole thing is B and this whole thing is H, then this distance is B over 3, and this distance is H over 3. And let me let's call this distance x centroid, x bar, and let's call this distance y bar, just to keep the formatting the same for all of these. So x bar for the right triangle is going to be b over 3. Y bar is going to be h over 3. And then the other thing we're going to need to know, and you don't see why yet, but this is the next thing we'll go into, is you'll need to know the area of that shape. This is going to be base times height over 2. The next common shape is a semicircle. Let's actually do a, let's do a quarter circle and skip the semicircle. So I'll call this distance x bar and this distance y bar. The calculation for x bar is 4r over 3 pi. Due to symmetry, you can tell that there's a line of symmetry along the line x equals y. So y bar has to be the same thing, 4r over 3 pi. And the area of that shape is pi r squared over 4. Most of what we're going to use are these, but I'm going to give you 2 other ones that you'll see 1 or 2 times in this class. So the first one is a well, let's just do one more. So a semi-parabola, half a parabola. This distance is x bar. The distance to the tip is y bar. The entire width of this thing is a, and the entire height is h. Then x bar is 3a over 8. Y bar is 3h over 5. And the area is 2ah over 3. All right. So why are we doing a quarter circle and a half of a parabola? when you might think a circle or a semicircle is more common than a quarter circle, and a full parabola is more common than a semi-parabola, half parabola. Well, the answer is that we're going to be able to use a sum formula to figure out that if you have half a circle, a semicircle, like imagine the whole top half of a circle, we can use symmetry to figure out that the centroid is just going to be on the center line vertically of that semicircle. Okay, so we don't have to worry about that. And the sum formula that I'm going to show you will show pretty much immediately that y bar for a half circle is going to be exactly the same as it is for a quarter circle. Okay, so that information is sort of contained in here. And it's the same thing for a parabola. If I continued the right side of this parabola, the x centroid would just be on the line of symmetry. So that's easy to find. And the y centroid would still be 3h over 5. Okay. So now let's talk about the sum formulas. So this is building up complicated shapes from simple shapes. And an example of this would be like if you're doing calculations about the motion of like a leg or something, a person's leg. The shape of a leg is complicated, but you can approximate it with a bunch of, a combination of simple shapes like this. Okay. And that's a really common thing to do if you're doing calculations with really complicated things. That's a pretty crude set of shapes to approximate it with, but you could divide it up as much as you want. You could imagine like taking any complicated shape and breaking it up into nearly infinitesimal, small, tiny little rectangular solids or triangular solids the way you do in, integration, like in deriving how to do integrals and stuff. And then you can just calculate the centroids of those individual pieces and use a sum formula. So here are the sum formulas that we're going to use. In 2D, x bar y bar is equal to 1 over the total area times the sum over all the shapes. So let's say there are n shapes. Of ai times xi, yi. Where ai is the area of the ith shape. And xi, yi is the centroid of the ith shape. And notice that this is just a finite version of the integral definition. If you look back at the integral definition, you have 1 over the total area times the integral of the centroid of the infinitesimal piece times dA. Okay. Now, if you make those finite, it turns into this. Okay. So this is the integral formula, just where the pieces are finite size. In 3D, it's similar, same thing, making all the changes that you would imagine. So it's going to be 1 over the total volume times the sum from I equals 1 to n of the volume of the ith shape times the centroid of the ith shape. So this is the volume of the ith shape. And this is the centroid location of the ith shape. So let's do 2 examples. Well, let's do 1 example in 2 ways. Okay, so we're going to calculate the centroid of a shape like this. So let's say it has a height of 1 meter and a width of 1 meter and a thickness of 1/10 of a meter. And we're going to do it 2 ways. So first, we're going to break it up into a rectangle like this and a rectangle like this. Okay. And use the sum formula to add those. Let me say to add area. And then the second way we're going to do it is we're going to calculate the big outer square. And then we're going to remove the material for the smaller corner square. Okay, so you can use this sum formula with, with positive areas, obviously, but you can also use it thinking in terms of like negative areas and removing material. So for part A, for both of these, we're going to use the same coordinate system. You can't do this until you define a coordinate system because that sum formula uses coordinates. So I'll use X and Y like this. So for rectangle 1, we have our coordinate system over here. This rectangle has a height of 1 meter and a thickness of 1/10 of a meter. And the centroid, using symmetry, is just right in the middle. So what are the coordinates of the centroid there? Well, what do we need? We need the area of that thing. That's going to be 1 times 0.1. So 0.1 meters squared. And then the location of the centroid is going to be in x. You know, we go halfway from the left end to the right end. So this is going to be 0.05. And we go halfway up the height, so that's going to be 0.5. And now we'll go to the second one. Okay, so I'm going to draw this thing that we're not taking into account. The rectangle we want is this one. And the centroid is right here. The coordinate system is down here. Okay, so what about the dimensions here? The length all the way from the left of the dot, you know, the dotted line on the left to the right end of this shape is 1. So what does that mean that the length of the shape we're considering is? Yeah, 0.9. And this thickness is still 0.1. So it's going to be well, let's do x first. From the edge of this rectangle, oh no, let's do the area first. So area is 0.9 times 0.1, so that's 0.09. And then the centroid, from the left end of the rectangle that we're considering, it's going to be a distance of 0.45. But to get to the left end of the rectangle, we have to move 0.1. So this is going to be 0.55. Does everyone see that? And then the y-centroid from the bottom of the rectangle is going to be 0.05. But to get there, we have to move up 0.9. So this is 0.95. And now finally, we can use this sum formula. So the centroid of this shape is 1 over the total area. The total area is just the sum of these two. Actually, let me write that. So the total area in this case is A1 plus A2. So that is 0.19 meters squared. So the centroid coordinates are 1 over 0.19 times the area of the first shape times its centroid location plus the area of the second shape times its centroid location and if you calculate that shape, oh, I don't have it because I made that up. Okay, so we got 0.1 times 0.05, 0.5 plus 0.09 times 0.55, 0.95. Then divide all that by 0.19, and you get a centroid for this shape of 0.287, 0.713. One thing that's worth making a mental note of on this is this centroid location is somewhere over here. Okay. So notice that there's no reason that the centroid needs to lie on material of the body. Okay. So it doesn't necessarily lie on a material point of the body. And that's even more clear if you think about the centroid of like a thin ring, you know, because of symmetry of a thin ring, the centroid has to be at the center of the ring, but there's no material there. Okay. And by the way, let's see. This is supposed to be a high jumper. In the late 60s, there was this revolution in the high jump. People had always gone up and done sort of a side, sort of barrel rolled over the bar of the high jump. And somebody came along and started running up, doing sort of a half turn on their jump and going over the bar backwards. And at first people were like, I mean, it looks sort of ridiculous if you're not used to it, you know, but this guy beat everybody. And it's like, why was this revolutionizing the high jump? The reason it revolutionized the high jump is because the people who barrel rolled sideways over the bar were basically having to get their entire center of mass over the bar. With good technique and this approach, let me draw the bar a little higher. Good high jumpers can get their entire body over the bar while their center of mass passes under it. And so physically, you're limited by how high you can get your center of mass. But if you can manipulate your center of mass to be lower than the bar, you're obviously going to go higher than the people who can't do that. And so that's why this guy's name was Dick Fosbury, and they call it the Fosbury flop. And there's nobody in high jump anywhere in the world that doesn't do this anymore. But the benefit of it relies on the fact that that center of mass doesn't have to be at a material point of the body. Okay, let's do the second approach. So now we're going to do this shape, and then we're going to do the smaller rectangle and use a subtraction using that sum formula. Okay, so the centroid here is in the middle of this square. The dimensions, this is 1 meter, this is 1 meter. The area of this shape is just 1. The centroid of this shape is 0.5x, 0.5y. And now the second body, we're going to so the dotted line is the material we're not considering. The coordinate system is still located at that outer edge. This height is 0.9 meters, and this width is 0.9 meters. So the area is 0.9 times 0.9, so 0.81. And the centroid location, if you start at the left end, then the centroid location is going to be 0.45 meters away. But to get to the left end, you first have to go 0.1. So this is again going to be 0.55. Going up from the x-axis, the thing has a height of 0.9. The axis is already at the bottom of that square, so this is just going to be 0.45. The total area, this time we don't get the total area from adding those two areas. You have to subtract. We're talking about the actual material area. So this is 1 minus 0.81, so 0.19 meters squared. And now using the sum formula with a subtraction, x bar, y bar is equal to 1 over the total area times the area of the shape, the big outer shape. So that's 1 times 0.5, 0.5. Minus the area of the shape we're removing times 0.55, 0.45, And obviously you need to get the same thing. I just want to make sure that everything I'm doing here is right. The numbers are all right. And yeah, you get back 0.287, 0.713. So the same thing as before. Okay.
As far as like double checking your answer, if you have time, doing it like 2 different ways is a good way to see like matching. Or is it just,
Yeah, that is a good way to check. Let's see. Let me think if there are any other. That is probably the best way I can think of to check. Yeah. Okay, so let's do an example. How would this come up? So let's say that we have a shape like this. Where this end is connected to the ground by a pin joint, and this is connected to the ground by a roller. And let's say that the whole mass of this thing is 10 kilograms. I need to give dimensions. So let's say that this is 1 meter. This is 1 meter. This is 1 meter. What are the reactions? How is the centroid going to come into this problem?
the math force.
Yeah, right. We have to find where the weight acts. So let's divide it up like this. I'm going to put the coordinate system here. And I'll call this body 1 and this body 2. Okay, so for body 1, the area is, we have, for this rectangle, we have a height of 1 and a base of 1. So 1 divided by 2, so 0.5. And now we have to think a little bit, you have to kind of think spatially here. We know that from the perpendicular side, in each of these two directions, it's going to be a third of the total distance. Yeah.
Since we defined our coordinate system as being in the middle there, for the area, does it not matter that we're going?
Correct. That does not matter. That does not matter. It only matters whether you're adding, like whether you're taking two pieces that add to form the total shape or whether you're removing material. Yeah. So we know that this distance is a third of that. Hold on. Running out of time. Okay, this is a third of that length, so that's a third. This is a third. And our coordinate system is down here. So x1, y1 is going to be, for x, negative 1/3. And for y, notice it's going to be positive 2/3. Okay. Then for the rectangle, oh yeah, we got to go to the other room. So A2 is 1 times 1. I guess I'm not going to finish this problem, but I'll at least finish the centroid. And the centroid of the shape is 0.5, 0.5. The total area is the sum of the two areas. And so the centroid of the whole shape is 1 over 1.5 times 0.5 times negative 0.3 repeating, positive 0.6 repeating, plus 1 times 0.5, 0.5, and for that, you get 0.5, 0.5 plus 0.5. 0.2 repeating for x and 0.5 repeating for y. So in other words, somewhere around here. Okay, that's all. See you in thermo upstairs.